Hi. So there's just one last concept that is left in quadratic equations, and that's the idea of a quadratic equation and expression in two variables, which we want to look at. So when we talk about a quadratic equation in two variables, let's say x and y, we are referring to an equation which will in general have second degree terms. Now the second degree terms in case of two variables could have three particular forms. You could have a term containing x square, you could have a term containing y square, and you could also have a term containing x into y. Similarly, when you talk about first degree terms, you could have two kind of terms. You could have a term containing x and a term containing y, and of course you could have a constant term. So this equation throughout the rest of the course, we'll be taking this as a general second degree equation in two variables x and y. This equation specifically becomes quite important when we start discussing when coordinate geometry comes into the picture. So when we start discussing curves like circles and conic sections, which include parabolas, ellipses, and hyperbolas, we'll be seeing that the equation of all such curves turn out to be of this particular form. That is to say that the equation of any circle, ellipse, parabola, or hyperbola in the xy plane happens to be a second degree equation in x and y. Right? Again, a is the coefficient of x square, b is the coefficient of y square, and so on. Now, typically, again, the way that for one equation, when you have one equation in x and y, when you have one quadratic equation in x, every solution is a value of x for which the equation is satisfied. Similarly, when you talk about a quadratic equation in two variables x and y, every solution over here will be a value of x and a value of y which simultaneously satisfy the equation, right? Which in other words, so therefore every solution for such an equation is taken to be an ordered pair x comma y. Right? So now of course you can talk about solutions under different conditions, but when you're talking about real solutions, by a real solution we would mean an ordered pair x comma y which satisfies the equation where x and y take real values. So typically when you're talking about the real solutions of such an equation, there are only three possible situations. Such an equation can have infinite real solutions. It could have only one real solution, or there's also a possibility that it might have no real solutions. So some simple examples are that. So if we look at this equation, x square plus y square equal to 4. Just to take a very simple example, when I talk about this equation x square plus y square equal to 4, some solutions are 2 comma 0, you have 0 comma 2, you have minus 2 comma 0, you have 0 comma minus 2. These are definitely some solutions, and there are a lot of other solutions also. So you could have root 2 comma root 2. So similarly you could have root 3 comma 1, etc. In fact, it can be shown geometrically that this particular equation x square plus y square equal to 4 will turn out to have infinite real solutions. So there will be infinite ordered pairs x comma y which together satisfy the equation. Of course, if you start imposing condition, if you only want to specifically talk about integral solutions, which would mean that x and y specifically should be integers, then the number of solutions might turn out to be infinite, it might turn out to be finite, that will depend on the exact equation. But in terms of real solutions, this equation definitely has infinite solutions. Then again, you might have a situation in which the equation just has one solution. So an example of such an equation would be maybe something like this. So if you look at this equation, obviously when you expand it, you will get a second degree equation in x and y. So the reason why you can claim that this particular equation has exactly one solution is because effectively what you were saying over here is that the sum of two particular squares is 0, which you already know can only happen if each involved term happens to be 0. So for this left hand side to go to 0, what necessarily has to happen is that x minus 1 must be 0, so x must be equal to 1. And simultaneously y minus 2 should also be 0, which means that y should be equal to 2. So this equation only has one solution, which is 1 comma, right? And again, a simple example of a situation in which you have a second degree equation in x and y which has zero real solutions, you could have something like this. If I replace the 0 by a minus 1, I have a situation in which I am saying that x minus 1 whole square plus 2 times y minus 2 whole square is equal to minus 1. Now obviously the sum of two squares cannot possibly be equal to a negative value for any real values of x and y, and therefore as far as the real solution is concerned, this equation does not have any real solution, right? So again, for such an equation, when you talk about every solution is an ordered pair, when we are talking about real solutions, that is to say when x and y happen can take real values, there are three situations possible. You can have infinite solutions, you might have a single solution, or there might also be a situation in which you have zero solution. Now typically, suppose if this equation happens to have infinite solutions, then what can be found out is a certain range of values that x and y can take. So infinite even in the case of infinite solutions, there might be situations in which x and y are limited to certain specific ranges. So one possible question that can be created is to actually find the range in which x and y lie. Right? So if you want to find the range of values that x can take, the procedure for that is pretty straightforward. What we'll simply say is that we'll say that we rewrite the given equation as a quadratic in the variable y, and then we'll impose the condition that the discriminant, since y is real, the discriminant of that equation in y has to be greater than or equal to 0. So what that will give us is a quadratic inequality in x, which when you solve that quadratic inequality, you will get the corresponding range of values of x. And similarly, if you want to find the range of values of y, you can rewrite the equation as a quadratic in x and then impose the condition that the discriminant must be greater than or equal to 0. Right? So let's just take some few examples and illustrate that idea. Right, so suppose this is the question. X comma y is given to be a real solution of this particular equation. And given that, again, so given that x and y are constrained or are related by this particular relation, you want to figure out the range of values that x and y can respectively take, right? So we'll first try to find the range of values that x can take. So as discussed, the first step would be to rewrite the equation as a quadratic in the variable y. So in order to do that, you can rewrite the equation in this way: 4y square plus. Right, so over here again I've rewritten the equation as a quadratic in the variable y, and now we'll impose the condition that the discriminant for this must be greater than or equal to 0. So x square plus 12xy plus 4y square plus 4x plus 8y plus 20 equal to 0. So 4y square plus 4y into 3x, that'll give me a 12xy plus 2, so that'll give me an 8y plus x square plus 4x plus 20. So 16 to 3x plus 4 square minus 16 into x square plus 4x plus 20. So that gives us a 16 9x square plus 4 right, so this gives us a quadratic inequality in the variable x, which we can easily solve using the wavy curve method that we've discussed before. So we get this as the range of values that x can take. So we're getting that x has to be less than or equal to -1, or x has to take values which are greater than or equal to 2. We can similarly easily talk about the set of values that y can take. So rewrite it as a quadratic in x. So again, divide by 16, simplify. Again, let's try to factorize it. I'll get 2y square plus 2y, so 2y into y plus 1. Again, we can use the wavy curve method over here. Get this as the set of possible values that the variable y can take. So let's say now this is the question. We are again given a second degree equation in x and y, and we want to prove that it has only one solution, and we also want to find a specific solution. So we can again proceed in the same manner by treating it as a quadratic in any one variable. So suppose we treat the equation as a quadratic in y. Right? So we've again rewritten terms as a quadratic in the variable y. So again what must happen is the discriminant must be greater than or equal to 0. So we'll get 8 plus 16, so plus 24x, and we'll get 16 minus 64. So 64 minus 48. So I can now divide by minus 3 throughout, but then the sign of inequality will have to reverse, which gives me that x minus 4 whole square is less than or equal to 0. Now at this stage we'll have to be slightly careful about this. Again, you want that x minus 4 whole square should be less than or equal to 0. But this is again a perfect square, so it obviously cannot be less than 0. The best you can do is that you can make it equal to 0. So the only condition satisfying the greater than or equal to 0 is to say that x is equal to 4. So for y to be real, it is turning out that x can only take one value, and that is 4. And for x equal to 4, we can reduce the equation. So the equation. So once we get that x can only be equal to 4, we can simply substitute x equal to 4 in the original equation. That gives us a quadratic in y, which again turns out to have only one solution. So finally what is happening is that x and y both can take one value each, and that kind of proves what you had to prove. So there is only one solution, and that solution is 4, 4. X must be 4 and y also must be 4. Right now in this question what's happening is that we've been given a second degree expression in x and y. So x and y over here, again we've already talked about the idea of range of a function, and specifically we've also seen the range of a quadratic expression. Now over here when I say that this is a function, now over here this is an expression which is dependent on both x and y. X and y themselves are independent variables over here. So you effectively have a function of two variables, and you want to be able to figure out its minimum possible value. Of course, it's easier to say that there won't be any upper limit. As you keep on increasing x and y, the entire expression will also keep on increasing its value, right? So there is no upper limit on as far as the function's value is concerned. Now, it might not always be possible to be able to figure out the range of any given second degree expression, right? But in this case, we can use the idea of completing the square to find the minimum possible value of the given expression. So just take a minute and think about how completing the square can be applied to solve this problem. So let's start by designating this expression as f of x comma y. So f of x comma y refers to some expression in x and y. X and y both are the independent inputs variables over here. So let me collect value terms containing x first. Now clearly for both these brackets individually, it's very easy to complete the square. So in the first bracket I can add and subtract a 1. In the second bracket I can add and subtract a 4. Sorry, there's a plus 10 over here. So finally, after completing the squares, I rearranged terms containing x and y and kind of completed the squares. So our expression in x and y reduces to this. You have a sum of two squares, x minus 1 whole square and y plus 2 whole square, and you have this value 5. And now let's use the same idea. Any given square will always be greater than or equal to 0. X and y over here again represent independent variables. So this term will be greater than or equal to 0. This term will also be greater than or equal to 0. So the entire expression is clearly greater than or equal to 5. Right? So for the given expression in two variables, the minimum possible value of the expression can be 5, as x and y take all real values. And specifically, when is the minimum value achieved over here? For that, x will have to be equal to 1 and y will have to be equal to minus 2, so that both these terms become 0. Now an important result for us is that there will be certain conditions, under certain conditions, this second degree expression x and y, we will be able to factorize it as a product of two real and linear factors in x and y. and that condition turns out to be this, right? ABC plus 2FGH minus AF square minus BG square minus CH square must be equal to 0. As long as this condition is true, then the given expression can be factorized as a product of two linear factors. The proof of this result is quite interesting. You should definitely try it on your own. It will involve the idea of taking a discriminant twice, right? So just try it. So basically what you will say is that, for example, let's say you treat it as a quadratic in the variable x. Then for that quadratic in x, the discriminant, which is a quadratic expression in y, must be greater than equal to that the quadratic expression in y itself must be perfect square, for which the discriminant of the quadratic expression in y itself must be 0. So as soon as you impose that condition, this turns out to be your result. Right, so over here again we have a expression in x and y, and there's a parameter m involved, and we want to find out the values of m for which this expression is factorizable, as it can be expressed as a product of two linear factors. And again, for such values of m, we actually want to go ahead and factorize the expression. We want to find those linear factors, right? So again, for the first part, to find the values of m, we just have to impose our result. But for that, let's just quickly compare and get the values of the coefficients. So a is 2, b was the coefficient of y square, so that's 3. H was half the coefficient of xy, so that is m by 2. G was half the coefficient of x, that is 0. F is half the coefficient of y, which is minus 5 by 2. And the constant term is minus 2, right? So we've compared the equation to the general equation and got the values of all the 6 coefficients. And now we just have to impose our results. So the first term was a into b into c, so that's 2 into 3 into minus 2 plus 2 times f g into h minus a f square minus b g square minus c h square should be 0, right? That gives us 6 into minus 2 minus 12 minus 25 by 2 plus m squared by 2 must be 0. So m squared must be equal to 25 plus 24. That's 49. So m can be plus. Right. So that's the answer to the first part. So m can take two possible values, plus 7 or minus 7. Now the second part of the problem is equally important, that you actually want to go ahead and factorize the expression. Right. So for m equal to 7, this would be our expression, and I've considered a corresponding equation. And let's try to use a quadratic formula to get the relation between x and y. So again, let's just treat it as a quadratic in any one variable, anything works. So suppose I treat it as a quadratic in x. So it's already in that form. So the discriminant again over here will turn out to be that will be 49 minus 24, that is 25 y square plus 40y plus 16. So our discriminant itself turns out to be a perfect square. This is something which will actually always happen. If you have a second degree expression and it is factorizable as a product of two linear factors, then when you treat it as a quadratic in one variable, the discriminant, the b square minus 4ac, that discriminant value will itself, which the discriminant value, which is a quadratic expression in the second variable, will itself turn out to be perfect square. So again, x by the quadratic formula now should be minus 7. This has my relation, and which gives us so when I take the plus and minus sign once each, I'll get these two expressions, and so my required factorization must be of the form, will be basically the product of these two factors. So the factorization of this expression therefore is the product of these two factors, which can easily be verified also. You'll get a 2x square term, you'll get a 3y square term, and minus 6y minus 5y. So when you multiply these two factors, you get this expression with m being equal to 7. So we can try to do a similar thing for m equal to minus 7 also. Considered again for m equal to minus 7, I've considered the corresponding equation. Again I'm treating it as a quadratic in x, so the discriminant again would be actually the form will turn out to be the same again, so you'll get 5y plus 4 whole square. So when I apply the quadratic formula, these two factors turn out to be the corresponding linear equations, and these must be the corresponding linear factors. So my factorization is right. So this should be the answer for the case when m is equal to minus 7. So we'll be looking at second degree expressions in x and y, in two variables x and y, more often when we start looking at coordinate geometry, because as I said that it turns out that a second degree equation x and y can represent all, it represents first of all a category of curves known as second degree curves, which includes circles, parabolas, ellipses, hyperbolas. It can also represent something known as a pair of lines, and under extreme circumstances it can also represent a single point, and it can also represent a null set in the xy plane. So that completes the concept on second degree equations in two variables. Thanks.